Welcome back. So this lecture is the first lecture we're going to have, or this video is the first video that we're going to have on the topic of topology. So I'm not going to define what a topology is right now. Let me say, for those who know what topology is, that we're going to be discussing mostly the topology of metric spaces. And every now and then we'll talk about more general topological concepts, but that will come later. Right now we're only worried about very basic things in the realm of topology, right? And pretty soon we'll be defining open and closed sets. Before I do that, I need to define open and closed balls. So here I have a metric space. X is a set, D sub X is a metric. An open ball around a point X of a certain radius R, right? So X is a point in the space, R is a non-negative real number. So the open ball is the set of all points X prime whose distance to X is at most R. And the closed ball is a set of points whose distance is at most R, but here you have strictly less than R, and here you have less than or equal to R. Right? So that's the only difference between these two definitions. Well, if I want to emphasize the role of the set and the metric, I'm sometimes going to write things down like having the subscript to be the metric space. Sometimes I only have the set, assuming that the metric is implicit. Oftentimes I won't have neither the metric nor the set here, or just assume that you understand which metric space I'm referring to. So, okay, where does this terminology of balls come from? Well, clearly it comes from ordinary geometry, right? So if you have a point in the plane here, that's your little x. If I give you a certain radius, we all know what the set of points within distance R from x looks like, right? So let's talk first about the open ball. So I'm talking about the set of all points within the Euclidean distance R from x. And I'm excluding the points at distance equal to R. So I only want distance less than R. So here's an open ball right here. Of course, when I'm assuming that the metric here is given by the L2 norm, right? So this is an open ball. What if I want a closed ball? Then I have to include everybody who's at distance R exactly equal to R from X. So I have to include this boundary here. We still haven't discussed what a boundary is in topological terms, but I think it's clear what I mean in this specific example, right? I'm just talking, there's just a circle that encircles a ball. And the ball is kind of funnily shaped. Luckily, as we're going to see, topology is very resistant to continuous transformations, resistant to continuous transformation body. There's not quite a Euclidean ball, but I hope you get the idea that what I meant is the region enclosed by a circle of radius r around x. Of course, I'm only talking about circles because I'm taking implicitly x to be R2. If it was an RD, the closed ball would be the region encompassed by a sphere of radius r around x, including the sphere itself, including the boundary, and the open ball would not include the boundary, right? So far so good. Let me notice that the shape of the ball depends strongly on which metric or which norm I picked here. So let me draw something that's kind of traditional. Here I have x2 again. I'm going to draw balls around 0, 0 of R2. Sorry, I think I said x2, then R2, just the plane, right? So here I have minus 1, 1 on the horizontal axis, 1, minus 1 on the vertical axis. And now I'm going to draw 3 balls for you, right? So I'm going to be talking about the balls of the LP norms. And here are what they look like. So here's the ball of the L1 norm. Well, you have to think a little bit to see why it's like this. Okay, what's the ball of I'm only going to draw closed balls. The only difference with the open balls is that you don't include the boundary. So what's this distance? The ball R2 1 is this set of points around 0, right? So the set of points x such that if you take the absolute value of the coordinates and add them, this is less than r, right? So this should really be r here. So that's the L1 ball. Well, the L2 ball, we know what it looks like already, but I'm going to try to draw it again, and hopefully this drawing is going to be a little bit better than the previous one. Well, I mean the L2 ball. Right, so the L1 ball is the interior of this diamond shape, this losange. The L2 ball is over here, so it includes the L1 ball of the same radius, L2 ball. And now let me consider the L infinity ball. The L infinity ball is different, right? So, okay, this is the L1 ball. What's the L infinity ball? I'm going to write it over here. And I'm just going to say set of x such that max, the largest coordinate in absolute value, is less than or equal to r. And what does that mean? Well, okay, I want the first coordinate to be between minus r and r. So any point of the L infinity ball of radius r has to lie between those two vertical lines, also has to lie between those two horizontal lines, because I want the second coordinate to be between minus r and r. So here's the L infinity ball. It's a square, like the L1 ball is a square, right? The L1 ball is a rotated square. But now it's not rotated anymore. Okay, so the good thing is that now, after this drawing exercise, we know what the balls look like in R2, and we sort of know what they look like in RD, right? So for instance, the L infinity ball is just a cube centered at 0 with side length equal to 2r, right? So this is a side length equal to 2r, the L infinity ball. The L1 ball is also going to be a cube, but somehow different in place in RD. And the L2 ball is just this round shape that we expect from balls, I guess, or at least if you play, well, Brazilian football, also called soccer, as opposed to American football. Right, so what about, right, so this is one example. Let me give you another example. So, well, there's one other example which is going to be in the homework assignment. So, is you take any set x and you define this discrete 0, 1 norm, a 0, 1 metric over it, right? So the metric that says 2 points are different are at distance 1 and a point at distance 0 from itself. So the exercise is try to describe what the balls look like in this metric, right? So let me erase this bottom line here. Move it a little bit lower. Okay. Yeah. The physicality of teaching in the kitchen is something that I haven't really gotten used to so far. Okay, other space. So let's continue our drawing exercise. So how should I try to draw balls in this metric? And now I'm going to do an open ball, right? CFR. So f is an element of C, so it's a continuous function. And, well, let's see what this means, right? So this is a set of all other functions. They're also continuous, defined over 0, 1, with values in R, such that the sup norm of the difference is less than or equal to R, or less than R, sorry, because I have an open ball. And let me say this in another way, which perhaps is clearer. And let's notice that these two ways are the same. why are these two the same? Well, okay, if the soup, right, what is the infinity norm? One more time. It's the soup of g of t minus f of t, absolute value. So if the soup is less than r, it certainly means that for all t in 0, 1, the distance between f of t and g of t is less than r. On the other hand, if this is true, well, we know that the supremum of this quantity is achieved by some t, because both f and g are continuous over the unit interval. But because the supremum is achieved, we know that the supremum has to be less than r. Therefore, the soup is less than r as well. Okay, so that's what a ball is, and let me try to draw it for you. I mean, to give you a way to think about it. Let me first plot an arbitrary f, but it turns out to be a pretty smooth function. But we can argue whether that's a good example of an arbitrary function, but let's leave it at that for the time being. Let me pick a t in here, and let me observe that if g belongs to this ball, this open ball, here I have the value of f of t. Here I have f of t plus r. Here I have f of t minus r. And my claim is that whatever g is, its values have to be in this strip. I mean, on this vertical line, right? So g, I don't know what it is. I mean, it's a function in this ball. I don't know what it is, but I know that its value at t is some point in here. Now what? Well, that's true of any t that I pick, right? So think about it. If I move this t, I have this strip, this band around the value of f of t. If I move it, it has to follow the graph of the function. So here's what happens. You have, if you draw this, I mean, throughout, you have this kind of, right? So you have this moving band around f, and you have kind of the upper part of it and the lower. I drew the lower part. Let me draw the upper part. As you can probably tell by now, my drawing really is kind of terrible. But I have this whole strip, right? So this is not quite the ball, right? It doesn't even make sense. That's just set in the plane. What I'm trying to convey with this picture is that any g whose graph lies inside this strip, and just to make sure, let me emphasize that the strip has length r both up and down. So this is r up, r down, and this, okay, this is really crappy. Okay, let me try to fix it a little bit. Yeah, r up, r down. So I have this strip around the graph of f, and any g that has its graph inside the strip is within distance r from f. So the ball around f is really the set of all functions g whose graph lies in this band or the strip of width r in the vertical direction that you draw around the graph of f, right? So I can maybe say something like this: if the graph of f is like this, the strip looks something like this, except that you have to be even more careful in drawing it than being here. So anything whose graph lies inside is close to f, is r close to f. Okay. All right, so after this sort of drawing exercise, which I miserably failed, I'll get back to more theoretical things, right? This is just to give you an idea that these things are not completely alien. And now I'm going to define what open and closed sets are, and we'll finish this video just by giving simple characterizations of both open and closed sets. So, okay, open and closed balls are not exactly the same thing as open and closed sets. So, I mean, my definition of an open set is going to be related to the metric x, or the metric d sub x, sorry. So keep that in mind. The definition of open and closed depends on the metric. Okay, so A contained x is open relative to d sub x, or according to d sub x, you could say, if for any point in A, you can find a kind of a protective bubble around X, that's around A, sorry, that's entirely contained in the set A. So the mental picture is you have A, and in order for it to be open, it must be true that for any point in here, you can find a perhaps tiny radius around it. Doesn't matter, this has to be positive, such that this little ball around 8 is entirely contained in the set capital A. Now, this is an open set, a closed set. Is a set whose complement is open. So the complement is just a set of points in the space X that do not belong to F, right? So that's the most basic definition that we have in topology, the definition of open and closed sets. It would be nice to know, and that's what we're going to do right now, that open balls are open sets and closed balls are closed sets, right? So, okay, this is a really trivial exercise. So we're going to show that any BXR with, okay, so let me start with something even more basic. Let me argue that these two sets are open and closed. Okay, why is X open? Well, given a point in X, I have to find a ball completely contained in X. But that's by definition, right? Balls are contained in X by definition. So any ball will do. Why is the empty set open? Well, if it was not open, then this statement would be false. There would exist an A such that for any positive radius that I pick, the ball is not contained in A. But how can that be if there does not exist an element in the empty set, right? So it's vacuously true. It's true because it cannot find an A in the empty set, and therefore it cannot find an A that violates this. Okay, if they're both open, then they're both closed too, because the complement of X is the empty set, and that has to be closed. The complement of the empty set is X, so that has to be closed as well. So, okay, so far so good. Now let's show that open balls are open and closed balls are closed. Okay, any open ball with positive radius is open. Now, look, you can define open balls with zero radius as well, right? The definition makes sense, but it turns out that such balls have to be empty, right? So distances are always greater than or equal to 0, so there's no way if you have less than 0 here, there will be no X prime satisfying this condition. So there's not much to be done with balls with radius zeros. What about radius greater than 0? Well, what do we have to show here? So, right, this is a candidate for an open set. So I have to prove that for any element in this guy, there exists, well, let me replace this guy by a delta, just not to mix up with this R here, right? So it's just a dummy variable. It's just say for all A, there exists a radius. So I have to find a delta, positive, such that B a delta is contained in BXR. So is that true or not? Is it the case that for any A I can find a delta? Well, it is, right? So I told you so. But how do you prove it? Okay, so, I mean, now we're going to use some intuition, and then we're going to try to turn it into a formal proof. So the intuition comes in the form of this picture, and I'm really going to try hard to draw a rounder ball here, right? So I'm pretending that my metric is Euclidean metric on the plane, but we'll eventually have to get rid of that. Here's the ball of radius R around X. I want an open ball, so I'm erasing the boundary. And then I have some point A here. And I want to guarantee that my radius delta is such that if I put a ball around A, and also an open ball, that this ball is contained in R. And it's sort of clear what that should be, right? So you want that this distance plus delta is not larger than r, right? So the distance between x and a plus delta should not be larger than r. Otherwise, this ball will sort of stick out of the ball around x, right? So, okay, let me define delta to be precisely what I have here. I want delta to be equal to x minus distance from x to a. And this is positive because a belongs to the ball of radius x around r, radius r around x, the open ball. So we know that for any point in the open ball, the distance from a to x is less than r. So this is positive. Okay. Now let's prove that this holds, right? So I claim that this is the right choice of delta. Let's prove that it works. So I have to prove that if I take an element b in the ball around a, I have to, or radius delta, sorry, I have to show that there's also an element here, right? If I want to prove that this set is contained in this one, what I have to do is prove that any element here is contained in the larger ball. Okay, so take b. Now, we know that the distance between b and a is less than delta because b belongs to the ball, the open ball. And now what? Now I just say, well, the distance between x and b is less than the distance between x and a plus the distance between b and a. That's a triangle inequality. What about this one? Well, okay, this guy, I'm just going to leave it here. What about this one? Okay, why did I put it strictly less? Okay, this is equal, right? But this guy here, I know that it's less than delta. So there's a strict inequality here. And delta was defined in a way that when I add these two things up, I get r. So let's see what happened. B is an element of the open ball around A with radius delta. And what I showed is that the distance between little x and B is less than r, strictly less. So B belongs to the ball around x of radius r, open. And that's what we wanted to do, right? So we wanted to prove that with this choice of delta, any element in this ball belongs to this other ball. And we're done. Given A, we found that there is a delta defined explicitly over here that guarantees this condition. So again, a set is open if any point in it contains a protective bubble that's entirely contained in the set. What we showed is that the open ball really is an open set, which is good to know. What about closed balls? Are they closed sets as well? Well, it's basically the same proof, but I'm just going to indicate the key steps. Well, it's the same proof, but in a slightly more awkward way. So let me. No, I don't need r greater than 0. I mean, didn't need it before either, but I mean, r equal to 0 is not much fun. So what is a closed ball with radius 0? It's just a single point, right? There's a set of x prime such that the distance between x and x prime is less than or equal to 0. Distance is always no negative, so that would mean that distance of x and x prime is 0. And by the axioms of a metric, we know that when that happens, x has to be equal to x prime. So the closed ball with radius 0 is just a single point x, but for larger r, it could be anything in principle. But okay, what we want to prove now is that the closed ball was closed, and how do we do it? Well, notice, okay, here we have our closed ball. Again, we live in this world of make-believe, where we're going to just use pictures to get, well, okay, quite the opposite, right? So we're pretending that our metric is Euclidean metric of the plane, but from that we'll find the right way of doing things that works, and we can prove formally that it works. So what we need to show? We want to show that F is closed, and the only way we know how to define closed sets right now is to show that the complement is open. And what does it mean? So what I want to show is that for any A in the complement of X, of the complement of the closed ball, there exists a delta such that the entire ball of radius delta is contained in the complement. And that's what we want to show. And I said that I'm only going to give a sketch, but notice that this is the same thing as saying for any A in X that does not belong to the ball, there is an open ball around A that does not intersect this closed ball. How do we find that? Well, I mean, it should be clear what I have, right? So let's say delta should be this size. And what is that? Well, that's the distance between X and A minus R. So the point is that we should try this choice. Distance between X and A minus R. Well, before before we had another delta. This delta makes sense because I know it's no negative. It's actually positive. And why is that? Well, if A is not in the closed ball, it means that the distance from X to A has to be bigger than R. So this minus this has to be positive. And now all you have to check is use the triangle inequality to say, suppose that B lies within this, in this ball of radius delta, right? So its distance from A is at most delta, well, strictly smaller. And then you have to check that that means that the distance of B to X is larger than R. And then you're done. But that I'll leave as an exercise. Well, it's a lecture notes anyway, and many other places. Okay. Right, so I want to finish by giving two very simple results about open and closed sets. One of them is very easy to state, and it's to say that it says that a set is open if and only if it's a union of open balls. Okay. Okay, it's open in X according to the metric D sub X if there exists a collection of open balls of X whose union is equal to A. What do I mean by a collection of open balls? I just say, here I have a set whose elements are open balls of X. Okay, that's what a collection of sets means in general. And I mean, collection of sets means just a set whose elements are subsets of X. A collection of open balls is a collection of subsets whose elements are all open balls. Okay, why is this lemma true, or this proposition true? Okay, for the main thing is that let's do some sort of reverse engineering, right? Suppose I tell you that a set A is a union of open balls. Which open ball should you take? What collection should you take? Well, let me observe that in some sense the natural collection to take is the collection of all open balls contained in A. Right, all non-empty open balls, right? So the ones with radius 0 are empty, so we don't care about them. So let me define B. So all of these guys are open balls contained in A. So they're sets contained in A. And it follows from standard set theory that the union of sets contained in A is also contained in A. So far I haven't really started proving this. I'm just saying that, right? So this is like a preliminary step where I'm saying, okay, take this collection of open balls, and this collection is contained in A. Okay, let me observe that if A is open, then this has to be an equality. Why is that? Well, look at the definition, right? So if A is open, then any element of A is contained in a ball contained in A. So, right? So for all A in A, there exists a ball, an open ball, contained in this collect, right? So it's one of the open balls contained in A, right? So for all A belonging to A, there exists one open ball belonging to this collection, such that A is an element of this open ball. And then we're done, right? So we're just saying, okay, we know that this union is contained in A. Now I know that any element of A is also belongs to one of these balls and therefore belongs to the union. So that gives me the opposite inclusion, right? So any element of the set is contained in a ball that belongs to this union. So any element of A is contained in the union. Okay, so that tells me that any open set is a union of balls. And how do I go in the opposite direction? Right, so now let's forget this collection because what I did here was to argue that if you have an open set A, you can find a collection of balls whose union is A. And the collection is the most natural possible. Just take any or every single open ball that's contained in A. What about the other direction? It's really a kind of a follows from the previous proof. Say that A is the union of balls like this. And now what I have to do is to given an element of A, we want delta greater than 0 such that B A delta is contained in A. Right? So if you manage to find such a delta for any A, then we know that A is open. Right? So I'm proving this direction right now. But that's pretty clear, right? Because if A belongs to A, which is a union, well, how do you get to belong to a union of sets? You have to belong to at least one of these sets. And this set is a ball, right? So B has the form B of XR. And by what we showed previously, this is an open set. We have that B, the open ball of radius delta around A is contained in B XR for some positive delta. Right? So R is greater than 0. I'm just saying, okay, one of the balls contained in this union has to contain a little ball around A. But then notice, if this ball is contained in one element of the union, then it's contained in the whole union, right? So to show that this ball is contained in this union, it suffices to prove that there is one set in the union that contains it, and that's precisely what we have. And then we're done. What we showed is that we wanted to show that some open ball with positive radius around little a is contained in capital A. And what we argued was that, well, one of these balls has to have A as an element. And in that ball, we can build a protective bubble, so to speak. Okay, as we're going to see, I mean, this sounds like an innocent observation, but it's going to be useful later. So it's nice to know that open sets are precisely the sets given by unions of open ball. What about closed sets? It would be nice to have a characterization of them, that does not depend on going to the complement, right? And it turns out there is one such characterization, which is that closed sets are precisely the sets that contain limits of sequences that are contained in those sets. Okay, that's a bit of a mouthful. Let me write it. F and X is closed if and only if for any subsequence contained in F, if X sub n converges to X, belonging to X, then it must be that X also belongs to the set. So any sequence that's contained in F and converges has to have a limit, its limit inside of F, right? So it's clear from this why the set of, say, that's something we know from analysis over R. Here's the real line. This is the interval of 0, infinity. And it's easy to see it's not closed according to this criterion, right? Because we take the sequence 1 over n, 1, 1/2, 1/3, it converges to 0, but 0 is not in the set, so that cannot be closed. It's also true and easy to check that all closed intervals in the real line are half closed, half infinite intervals are closed sets with the standard metric, right? Which is always a metric we assume if I don't say anything. Okay, so that's sort of the sequential characterization of closedness. Okay, so I'm going to prove, first of all, a direction that goes from here to here. Okay. So assume F closed, and you have a sequence in F that converges to some X in X. Right? So what does that mean? It means that for all delta, there exists an n notch. For all n greater than n notch, distance from x sub n to x is less than delta. Okay, the delta is pretty small, which perhaps appropriate. Hopefully you understand that this is a delta. Okay, right, so here I just wrote what it means to say that x sub n converges to x. Now F is closed, right? So here's F. What do we want to show? We want to show that this point little x belongs to the set F. And now, let's take a point outside of F, and this set is an open set, right? What do we know about the complement? That it's open. I just wrote it down. So there exists a delta such that BA delta is contained in XF. And what does that mean in terms of our sequence? Well, our sequence is entirely inside of F. And that means the sequence cannot enter this open ball around A, right? So for all n, xn belongs to F, and x sub n does not belong to this ball. What about that? Well, that means that no single term of my sequence, any term of my sequence whatsoever, cannot be at distance less than delta from A. But we know that if A was the limit, then there would be values of n such that x sub n is at distance less than delta or less than whatever you want from Yeah, sorry. So here maybe I should have written this with less than delta because that makes it immediately clear. It's the same, right? But let me say again. If x sub n is a term of my sequence, it lies in f. Therefore, its distance to a is always greater than or equal to delta. And from this, you can see that a cannot be the limit. So what did I show here? I showed that any point outside of f cannot be the limit of x, of the sequence, sorry, cannot be the limit of x sub n. Therefore, it must be that x, the limit, belongs to f. To recap, I started out by assuming that f is closed, therefore the complement is open. And what I showed is if I have a convergent subsequence whose terms lie inside f, the limit has to be inside f too. Because points outside of f, they have a protective bubble that does not intersect f, right? That's what's written over here. That's half of what I have to prove, then I have to move in the other direction. Okay, right, so again, I'm going to start by assuming that I have this property of sequences, and I want to prove that f is closed, so sorry. And this I'm going to write in yellow just for change. Okay, so I'm going to assume this, that for any sequence that converges, if the sequence is contained in f, the limit has to be in f, and I'm going to prove that f is closed. So what we want to prove is that x sub f is open. Okay, so we're going to prove it by contradiction, so assume not. What does that mean? It means the negation of this statement. It means that there exists an A such that for any delta that I take, the ball is not contained in x sub f. Or, that's actually equivalent, but you only need it in one direction. What does it mean that the ball is not contained in the complement of f? It means that any ball with positive radius around A has to contain a point that does not belong to the complement, therefore belongs to f, right? Okay, so let me put it like this. And I'm only going to care about balls of radius of the form 1 over n. So there exists an A such that for all natural numbers n, the ball of radius 1 over n around A intersects f. That's the same thing as over here if I take delta equal to 1 over n, which I can do, right? Because for any positive delta, I have a non-empty intersection. Right, okay. Now take x sub n to be some point in here, right, for each n. All the x sub n belong to f. And we can see that the distance between x sub n and A, well, it's greater than or equal to 0. And look, if x sub n is in a ball around A, the distance between x sub n and A cannot be larger than the radius of the ball. Actually, it has to be smaller because this is an open ball, right? X sub n is here, therefore its distance is smaller. And you see that the distance between 0 and something that goes to 0, therefore x sub n converges to A. And here should be the complement, right? So I'm writing everything wrong. Okay, this is my set A. That's the open set that I have. X sub n converges to A. And by assumption, when a sequence of points in F converges to a limit, that limit has to belong to F. And now I have my contradiction, right? I said, we want to prove that x sub f is open. We assume it's not open, then there must be a point in there such that any ball of positive radius around A intersects f, so that's what's over here. From that, we built a sequence of points of f that converge to this point A. But if the sequence converges to A, and we know that the limit of a sequence in f has to be in f, then A has to be in f, but that's a contradiction. Because we started out by assuming that A, right, by taking A to be an element in the complement of f. Okay, what did we accomplish? Again, we started out from this criterion, say f is a set that satisfies this. And we showed that a set that satisfies this has to have an open complement. And by definition, a set has an open complement if it's closed. So we have proven that any set satisfying this is closed. We had already proven the other direction before, so now we have an if and only if. A subset of X is closed if and only if it's sequentially closed, meaning that convergent sequences in the set also have limits in the set. And that's it for now. Thank you.